Hello again. So I'm going to take you through how to handle twinned crystallographic data in the program Crystals, and just show you a quick example of that. So start Crystals in any folder you like, and then go to the Help menu, choose Workshop/Demo, Proceed, and then we're going to choose Workshop Structure number 5, Tin Twin. This is a tin trimethyl hydride provided by Simon Parsons and suffers from non-merihedral twinning. This means that there are at least two domains in the crystal. They both contribute their own diffraction pattern. We've managed to index on one of them, and the other diffraction pattern is causing a contamination of the first diffraction pattern, so the measured intensities are not what we would expect. But let's import the data and discover that for ourselves. So we'll read in the INS file, the HKL file is read in automatically, we look at the data, it seems okay. The merging R is a little bit high, but maybe it's just bad data. It's p-bar 1, there's no systematic absences, and everything else kind of seems in order. Right, let's solve the structure. We run superflip, it likes the space group, and here is the structure. So we're expecting a trimethyl hydride, so there's some noisy peaks here in the electron density map from superflip, so we can get rid of those, and they will tend to be the lowest numbered peaks. So 1, 2 and 3 are our real methyl peaks, 4 and 5 are just noise. So there is our structure, tin trimethyl hydride. We haven't found the hydrogens yet. So we start refining the structure. The R factor is already about 8%, drops down to 7%. We go to anisotropic refinement, and it kind of looks alright, but there's some artifacts here. This the directions of the ellipsoids don't quite tally with how we'd expect this the molecular motion of this material to behave in the solid. And if we try and do a difference map and add hydrogens, we'll see it's quite noisy. So we don't find the hydrogens on the methyl groups. Possibly that's the hydride, but we don't really. There's not really enough information there to tell. Okay, so let's look at the. So we're away from the guide now. We're going to look at the FOFC graph. So it's the second item down on this Analyze menu, and it shows us a plot of every reflection. This is its measured amplitude, and this is its calculated amplitude from our model. Now, what you tend to see with twins, and sometimes it's a bit more marked than this, is kind of a baseline up here. There's not many points below it, but there are a few points above the line, and those are due to the contamination from the second domain. So we're going to run an analysis called a ROTAX analysis, and that's going to look for twin laws, so relationships between those bad reflections that we just saw in that graph that can be explained by a second twin domain, and so that means every reflection that's under the operation of this rotation has to be contributed to from an existing reflection in the same crystal system. And it gives us a choice of 4 twin laws. They're all quite similar. There's a rotation around the A-axis, and there's a rotation around some kind of diagonal. And the figure of merit here, the lower it is, the better. So usually it's a good idea to start with the lowest figure of merit. And there'll be 2 that are very similar, and they're just rotations around very close directions. Anyway, pick the lowest one, click Apply Twin Law. We can back up our DSC file if we want, so we can come back to it later, and apply the twin laws. So now when I look at my list of reflections, you can see this column here tells you which reflections are contaminated by some overlap from the second domain. So 1, 2 indicates 2 domains contributing to that reflection. A 1 means it's not affected by the twin. Okay, so what happens now? Let's do some refinement. So our R factor is 7, our weighted R is 23. I click OK, do the refinement, and the R factor drops 4 to 4 and 20. So that's quite a spectacular drop. We've basically only added one parameter, which is the twin component to twin fractions, so they're called the twin element scales here. It tells us how much of the contribution to a reflection is from the first domain and how much is from the second. Okay, so as long as it gives us a big effect in our R factor, then we can be reasonably confident that's a good twin law. If I look at the FOFC graph now, it looks much straighter. There's still a few outliers here. This could be because there's another twin domain, or it could be because we haven't got our twin law and the amount of overlaps quite right. But that's the general principle for dealing with twinning. We'll carry on now with the refinement, add the hydrogens, and so on. Okay.